So before we do the prac on using PhreeqCi and looking at chemical speciation ourselves, it's good to have some background. So this presentation is designed to do that, help you understand how concentrations of different species are calculated in natural systems using other numbers, that is the equilibrium constants for the reactions. Here's an example from a different context, from seawater, looking at the variation of iron concentration in solution. That's on the vertical axis in nanomoles per litre, and the concentration of dissolved organic carbon in micromoles per litre along the horizontal axis. And as DOC increases, we see a corresponding increase in iron concentrations in solution. I don't really like the use of the term solubility there, because that solubility is really a property of a solid. However, anal retentive chemistry geek aside, it would be useful therefore to know what's going on here, and if we could measure the equilibrium constants for formation of an iron dissolved organic matter complex, we would then have enough information probably to simulate this with a chemical equilibrium model, given that we know some of the parameters of seawater like pH and major iron composition. So we're going to have a look at what we might need to do with that. And there's another useful factoid for you, that dissolved ferric iron concentrations in ocean water would be a couple of orders of magnitude lower than we see here, given that no dissolved organic matter is present. And that value would be is calculated again on the basis of the solubility of ferric minerals like ferrihydrite or goethite or hematite. So let's carry on. That preceding example hopefully was enough justification that speciation is important, but of course in soil systems speciation is just as important and probably more complicated to calculate. What we'll do is a simplified version of speciation calculations valid for soil systems, and we can discuss perhaps how we might make them more complex. Nevertheless, we've been talking about bioavailability and mobility of elements or substances in natural environments, including soils, and I think we've made the case to some extent that the speciation of elements determines bioavailability and or mobility, probably both. So for example, for a carbonate species, the pH of a soil determines whether we have dissolved carbon dioxide or carbonic acid or bicarbonate or the carbonate anion. Apologies for not balancing this equation in terms of oxygen or hydrogen for that matter, but the fact is that the proportions of these species also affect the pH, because they're equilibrium reactions and everything is coupled to everything else in the system where that reaction is occurring. So we're going to try and get a handle on that as we go. So we need some basic concepts to understand speciation. First of all, we need to understand what the difference is between chemical species and total concentrations. So we'll go through and do that. We need to understand the concept of a mass balance for each element, so simplistically the sum of all the possible forms of that element. We need to understand what equilibrium constants or related values such as formation constants or stability constants are. Some of it may be revision. I don't want to assume that it is for some of you, particularly as some of you did confess to not having a lot of chemistry background, so hence the reason we go through it at the beginning for everyone, and how to write equilibrium expressions, which may or may not be a revision again. So equilibrium expressions first of all. So as a chemical reaction will simplistically at least go from reactants to products, and we assume in chemical equilibrium theory that they're in some sort of dynamic equilibrium. And the position of equilibrium depends on basically the the free energy difference between reactants and products. And that gets quite complex and involves at least the first two laws of thermodynamics. And I guess one of the key principles that we need to understand from our point of view is that we can have many reactions in equilibrium simultaneously. Often they will share reactants or products, and that creates the complexity in the system, that reactions are coupled with one another, and therefore we can't change one without everything else changing pretty much. So usually we use the symbol K, or uppercase K, for an equilibrium constant. So K for constant, not really, but it's just a tradition. So the larger the K value, the more the reaction travels in favour of the products, or the right-hand side of the reaction. And because often we're using very large numbers, often we use log K values. So, for example, if the equilibrium constant is 5 by 10 to the 20, which is not unusual to have a log K, K value that large, log K value would be 20.7, the log of 5 by 10 to the 20. Okay, sometimes for very small values of an equilibrium constant, which again are not that uncommon, for example those which describe solubility, and the example here is the solubility of lead sulfide. The pK or system is used, analogous to pH. pK is minus the log to the base 10 of K, just in the same way as pH is minus log to the base 10 of hydrogen ion concentration. So if our K value is, let's say 3.16 by 10 to the minus 28, which is the K value for dissolution of lead sulfide, then our pK value is 27.5. Okay, so if we know the reaction, we should be able to derive a value for the equilibrium expression. And in general, we see the procedure shown in the top two lines. Now, just a note about this, we are interested in the concentration of different things, but in chemistry we use the activity, which is, if you like, an effective concentration modified by a parameter called the activity coefficient, which allows for the changes in chemical reactivity as some system conditions change. And in solutions, mainly that's to do with ionic strength and ion-ion interactions. So for going back up to the top here, for a typical reaction where two reactants are in equilibrium with two products, the reactants A and B, and products C and D, and they each have a mole ratio associated with them, little a for reactant A, and so on. The equilibrium constant is defined by the product of the product activities or concentrations raised each to their power of their, what we call stoichiometric coefficient, the number of moles of each in the balanced equation, divided by the product of the reactant concentrations, again each raised to the power of their stoichiometric coefficient. Right, so here's an example for you. Aluminium ions in any solution containing water will hydrolyze, that is, they will react with the water, and so that the water and the aluminium ions exist in equilibrium with an aluminium hydroxy complex, and that is a reaction that dissociates the water molecule. Alright, so we can write the equilibrium expression like this. So the concentration of this aluminium hydroxy species, not raised to any power because there's no stoichiometric coefficient in front of it, times the activity of hydrogen ion squared divided by the activity of aluminium 3 plus ions. Now we don't conventionally include water in that. We conventionally define the activity of pure phases, solids or liquids, as being equal to 1. So solids and liquids get excluded effectively from the equilibrium expression. Alright, we'll go on to give another example. Here's one that we'll build on a bit later on, and particularly the different equilibrium reactions related to carbonate and water. And we're using water systems at present because they're easy to understand. But here's for calcite dissolving by this reaction, calcium carbonate solid giving calcium ions plus carbonate ions. The KSP value, again, it's the product of the product concentrations raised to the power of their stoichiometric coefficient, which in both of those cases is 1, and we would normally divide by reaction concentrations because it's a pure phase, a pure solid. It's 1, so the KSP value is just the ion product. Alright, equals calcium ion activity times carbonate ion activity. Now, in most cases, we can assume that activities are approximately equal to concentrations. We'll get onto that a bit later. Some reactions are kind of a sequence of 2 reactions. They're what we call linked equilibria. So for hydrolysis of iron 3+ in water, so it's very similar to the reaction we saw before for aluminium, but in this case we're taking the reaction all the way through to the solid phase, which is probably something like ferrihydrite. Iron 3+ reacts with 3 hydroxide ions to form FeOH3 as a solid. So we can derive an equilibrium constant for that reaction as before, but the hydroxide has to come from somewhere in the system, and usually it comes from water in natural systems, in fact almost always. So we need to take into account what we call the self-dissociation of water, and which is pretty accurately known. We call it Kw. And the complete reaction, where iron reacts with water to form ferric hydroxide plus H+, has an equilibrium constant, which is just the product of the 2 reactions contributing to that, and that's a general outcome for manipulating log K values, right? Or K values. So it's the product of the K values, and if we worked with logs, of course, log K for hydrolysis, that's this reaction here, would be log K for precipitation plus log K for water, because if we multiply untransformed values, we'll be adding log transformed values. That's just mathematics. Okay, pH buffering, something that's useful to understand. Strong acids like hydrochloric and nitric acid, obviously they ionize completely in solution. In contrast, weak acids like carbonic acid, phosphoric acid and its associated conjugate bases or anions, and organic acids like, in this case, acetic acid or ethanoic acid, if you want to be really fussy about it, they ionize partially. So we see acetic acid in equilibrium with acetate, the anion, and hydrogen ions. So a solution of a weak acid or base contains its conjugate, alright? So in other words, acetic acid solution will always contain acetate, and vice versa. So that means the solution can react with either H+ or OH-, and it will usually be a buffering solution if both of these ions are present simultaneously. Now we can express this mathematically, and we'll get there with a few steps. First of all, the acid dissociation constant, so Ka, just a special example of an equilibrium constant for this reaction here, is expressed like this. We're using square brackets in this case to denote concentrations. Being a bit lazy about that, but it's a valid approximation in most cases. Has a certain value which is well defined, 1.8 by 10 to the minus 5. And we can do a little bit of algebra on that and rearrange it so that pH is equal to the acid dissociation constant plus the log of the ratio of the conjugate base to the conjugate acid. So if and that means if this ratio is 1 and the log of 1 is 0, then if pH is equal to pKa, then the concentrations of these two species must be the same. Alright, or similar. Right, 4.74 of course being minus the log of 1.8 by 10 to the minus 5. So we're going to have another look at pH buffering in a bit more detail using this, what we call a pH predominance diagram of a type anyway, and it's worth explaining this type of diagram. So we have a plot here of the fractional contribution of each species to total phosphate of the different phosphate species related to dissociation of, in this case, phosphoric acid into dihydrogen phosphate, monohydrogen phosphate, and just the raw orthophosphate anion, expressed as a function of pH. And so we can see that at low pH, in fact very low, unusually low pH, and wouldn't be seen in natural systems at least, then we have undissociated phosphoric acid, and as the pH increases, the fewer hydrogen ions are in solution, and that allows dissociation of phosphoric acid. So we see that being less important and disappearing effectively from the solution about pH 4 at the expense of the dihydrogen phosphate anion, which then becomes the predominant species at about pH 4.5, and which, as pH increases further, then drops off in concentration at the expense of the monohydrogen phosphate anion, again because the increase in pH lowers hydrogen ion concentration and allows further dissociation according to chemical equilibrium principles, and at very high pH we see the orthophosphate anion. So just a word about that, where we'd see most soils sitting, say, between pH 4 and 10. It's these two species of phosphate that are most likely to be found. So at lower pH, the dihydrogen phosphate anion; higher pH, the monohydrogen phosphate anion. So the same would be true for natural waters, and according to what we saw before, using pKa values, where we have roughly equal concentrations of an acid and its conjugate base, so around about pH 2 and a bit, or because this particular acid can dissociate 3 hydrogen ions successively, just about pH 7.2 and about 12.4, we see that we should observe buffering there, because we've got both the acid and conjugate base, or base and conjugate acid, present in the system simultaneously. And that is in fact what we observe. So if we plot the buffer intensity on that curve that's just overlain, we see the peaks in buffer intensity occur pretty much exactly where we'd expect them to, where we have both an acid and its conjugate base present simultaneously. So if we do a titration of phosphoric acid, then, and you may have seen this sort of thing before, we get something like this occurring. So in this case we start off with a solution of phosphoric acid, and we add little by little a strong base, sodium hydroxide in this case. We titrate it, so the overall effect is that the more base added, the higher the pH gets, but it doesn't follow a linear trend. We see the pH not changing much as we start to generate a solution which contains phosphoric acid and its first conjugate base, or the singly dissociated anion. And when we have almost only dihydrogen phosphate present, the pH can rise up again until we get significant amounts of monohydrogen phosphate in the system, so we get more and more buffered. The midpoint is about where those two species are equal, and so on, going up. We see the last phase of buffering, or a flat titration curve, flattish anyway compared with the other bits, where the monohydrogen phosphate and orthophosphate anions are present in similar concentrations. So if we relate that to our curve turned on its side, we can see that we see the buffering at those pHs. So hopefully the pH scales on each part of the diagram match somewhat. We can see buffering occurring there. Okay, so we'll